Now let us learn the method of mathematical induction. Now it is a method of proving certain types of statements in mathematics, often defined for natural numbers. So what we have to understand here is it is one way of proving mathematical statements. Like you must be aware of some other methods like proof by contradiction, where we assume something which is opposite to what is to be proven and then arrive at a result which contradicts the assumption. So that was a method of contradiction. Here we have another method called as method of induction. Just to give a brief idea of the basic concept of induction, let us take an example of what is called as domino effect. So by domino effect, what we mean is, let us consider that there are several dominoes which are kept in front of each other in a line, right? So like they are kept very close to each other. Now our aim is to make all the dominoes fall down, right? But in that case we don't want to manually make each and every domino fall down. What do is we just make the first domino fall down manually, and when it falls we ensure that it will fall on the second one. That will in turn ensure that it falls on the third one, and so on. So that means if we do two things, that is, if we ensure that the first domino is manually fallen down, and if we ensure that any particular domino is connected to the next domino, then it would mean that ultimately all the dominoes will fall down, right? So this is the crux of method of induction. Now let us see how this can be translated in actually using the method of induction, right? So let's go ahead and see the two important steps that we must perform to prove a certain statement by using induction. So when any sum is given to us to be proven by method of induction, we proceed as follows. So here is the procedure to use the method of induction. First, let us consider the given statement as what is called as P of n, that stands for a proposition in n. That means something which is to be proven, that we call as proposition, where n is a natural number. Now as a step 1, we show that P of 1 is true. Now that is analogous to falling down the first domino manually by hand. So it's like that. We take n equal to 1 and we show that LHS and RHS are equal to each other. Now the next step is very important, that is, we show that if P of k is true, that is, k is some arbitrary number between 1 and n. So if the proposition is true for some value k, then it has to be true for the value k plus 1 also. So if we are able to prove this, then it would mean that it is true for all the values of n. So that means what do we do essentially is for n equal to 1, we prove that the statement is true, correct? Then by showing that the statement is true for k, we prove that it has to be true for k plus 1 also in second step. So what it means is, if k were equal to 1, then that means it must be true for n equal to 2 also, because that's what we have proven just now. Now interestingly, we can now take k equal to 2, and that would mean that it must be true for k equal to 3 also. And if we take k as 3, then it would mean that the statement must be true for 4 also, and so on. So it starts off a kind of chain reaction, and then it would automatically mean that it is true for any value of n, right? Now let's do a sum so that this whole procedure will be clear. Now here is one example, that is, we have to prove that 1 plus 2 plus 3 plus so on up to n is equal to n into n plus 1 upon 2, where n is a natural number. So in other words, we know that the sum of natural numbers, first n natural numbers, is n into n plus 1 upon 2. So here we want to prove it by induction. So first of all we say that let the proposition in n stand for the statement that is to be proven. So whatever statement is to be proven, we call it as P of n. See, we can go on putting n equal to 1, n equal to 2, n equal to 3 and so on, and we will always find that the left hand side is equal to right hand side. But then this has no end because there are infinitely many natural numbers. So we can't keep on doing this forever, and therefore there is a need of the other method, which is nothing but induction. So moving ahead, as a step 1, if you remember, the step 1 was to prove that the given statement is true for n equal to 1. So therefore if you put n equal to 1, then on left hand side n equal to 1 means we have to just take one term, and that is nothing but the number 1 itself, right? On right hand side, putting n equal to 1 gives us 1 into 1 plus 1 upon 2, correct? So we put n equal to 1 in the right side. So 1 plus 1 is 2, which gets cancelled, and ultimately we get 1. So since LHS and RHS are equal, we say that the proposition is true for n equal to 1. So that means P of 1 is true. So it's like we have fallen down the first domino manually. So we can do n equal to 2 also, and we will still be able to prove that 1 plus 2 is equal to 2 into 2 plus 1 whole upon 2. You see, 2 gets cancelled and 2 plus 1 is 3 and 1 plus 2 is also 3. So it's not wonder that it is coming out as true, because anyways that is what we have to prove, but being infinitely many numbers we have to do it smartly. So let's go ahead and go to the step 2, right? So now here we assume the truth of P of k. So we say that if for the time being we assume that P of k be true, then what it means is 1 plus 2 plus 3 plus so on up to k will be of course equal to k into k plus 1 upon 2. Alright. Now assuming that, what is that we have to prove? Now we have to prove that the proposition is true for P of k plus 1. That is the next element which is coming after k. So that means what is that we have to prove? That means we have to prove that 1 plus 2 plus 3 plus so on up to k plus 1. Now the last term will be not k, but it will be k plus 1, because that's the proposition. And this we have to prove to be equal to, wherever there is k, we have to put as k plus 1, isn't it? So we have k plus 1 into k plus 1 becomes k plus 2 whole divided by 2. So this is what we have to prove. Now let us take one term which comes just before k plus 1, and you will agree that it is nothing but k, isn't it? So when we start with the LHS, you see the sum of terms from 1 to 3 up to k can be replaced by k into k plus 1 by 2, isn't it? Because that is what we had assumed, the truth of P of k. So whenever we replace the sum of first k natural numbers by k into k plus 1 whole upon 2, now only one term remains to be added into that, which is the last term, which is k plus 1. So therefore we add k plus 1 to it. Now you can see that this can be easily simplified, that is, if we take k plus 1 as a common term from both of the terms, or we can even take k plus 1 upon 2, whichever way, then in the bracket what remains is k plus cross multiplying we get 2. And you see, interestingly, we have got the required right hand side. So what it means is, whenever P of k is true, it has to be true for P of k plus 1 also. So combining that with the first step, it is clear that P of n is true for any value of n as a natural number. So this is how we have proven the required statement using the method of induction.